So we started out by having the structure of the receiver being given to us. It was a linear sampling receiver followed by a threshold detector. Now, that allowed us to introduce many concepts, including the concept of maximum likelihood and maximum a posteriori probabilities for the maximizations for different strategies in the detection part. We also looked at the matched filter being the form of the filter in the linear receiver, so that the best strategy was to match the receiver filter to the shape of the symbols being transmitted. So these were two key ideas that we wanted to get out in the front very early. But now we're going to step back and in many ways start over, and instead of being given the structure of the receiver, we'll sort of develop an intuition and understanding for why this form of the receiver is what is used. And in order to do that, we're going to need a mathematical technique known as signal space. And so now I introduce you to this concept of signal space. So signal space is covered in our SCLAR text for the class. It's covered in section 3.1. And I'll also be discussing the Gram-Schmidt process, which is not covered in the textbook, but there's many online resources that discuss this technique for finding a basis for signal space. So let's get started. So again, our conclusions to date: we know how to maximize the a posteriori probability, we know how to maximize the likelihood, and we know that we should use a matched filter in order to maximize the signal to noise ratio. We have found so far that the waveform shape itself is arbitrary in this analysis we've done to date. But we've only considered two symbols, only binary, and we have not considered different shapes, different waveform options that we might have. Instead, we've just said whatever waveform we end up with, we should match it at the receiver. So now we'd like to generalize our results, and we'd like to address not just binary signaling, but what we call M-ary. So there's an arbitrary M number of symbols in the constellation, in the alphabet. And we'd like to have the mathematics to do the analysis, and we'd also like to find out what the structure of the receivers will be, and how that structure is determined by our choice of waveform. So we have a free choice of waveform, but it's possible that different choices of waveform are going to lead to different kinds of performance. Certainly, whenever we fix the waveform, match filter makes sense. But anyway, we have to go beyond that simple conclusions. And we introduce now this idea of the bit error rate. I mentioned it briefly earlier when we were talking about the ML and MAP strategies. So the acronym is BER, and that stands for bit error rate. And that will be the gold standard for determination of the performance of a system, of a digital communication system. And if you remember, I said there are three criteria that we're going to use to say how good a communication system is. Power efficiency, spectral efficiency, and the cost or the complexity. So bit error rate is our way of quantifying the power efficiency. If I fix the power at a certain level, if I fix the signal to noise ratio to a certain level, is one choice of waveform going to give me less bit error rate than another choice of waveform? And this kind of question that we're going to address is going to be much easier to answer when we use our signal space analysis. So our motivation for the use of signal space is that it gives us the mathematics to attack either the maximum likelihood or the maximum a posteriori strategies. So we've seen an introduction to them that was simple to give us some feeling for these manipulations, and now we're going to be doing something a little more general. We will be able to get decision rules that may be more complex or similar to this comparison with a threshold. So we're going to use the mathematics of maximum likelihood and maximum a posteriori and push that to decide what kind of decision rules do we get in those cases. Not necessarily with the approach we used previously. And the signal space, very importantly, is going to give us the ability to develop some geometric intuition A signal space is a vector space. And we use vector spaces to represent our 3D environment. So we have a lot of intuition on this geometric interpretation of vectors, etc. And so that will be able to be applied to different types of modulation. And digital communications is full of a great variety of modulation formats. And being able to determine why one may be better than another in a given circumstance, it's going to be a lot quicker to understand by exploiting our geometric intuition. Finally, of course, I said the bit error rate is the gold standard for evaluation of the performance of a system, and so we're going to have the tools we need to do error probability calculations when we work in signal space. So signal space is a vector space. It's a vector space which has a finite dimension, which means it's much easier to attack. If I have m symbols in my alphabet for my digital communication system, that means that this vector space to represent the signals, the signal space, will have at most dimension m. It's an important distinction because if we were to look only at the noise signal space, the noise vector space, that would be a space of infinite dimension. So of course our received signal is the sum of signal and noise, and so we're going to have to address this, but the representation for the signals is always in a finite dimensional space because we have a finite number of symbols. So vector spaces, signal spaces, how are they related? So here we have a three-dimensional representation of a vector space, a three-dimensional vector space, and of course it looks similar to what we've seen before, except that in our geometric interpretation of vector spaces in real space, we would have like an x-axis, a y-axis, a z-axis, but here you can see that the axes are actually labeled as functions of time. So here is c1 of t as the label on my first axis, c2 of t is the label on my second axis, and c3 of t as my third axis. And now in this vector space, which is defined with time-varying signals as the basis vectors, I have an arbitrary vector which has been drawn here, and this vector in this three-dimensional space represents a signal which is a waveform, which is a time-varying waveform. So how do we do this? How can we take time-varying signals and represent them in a vector space? That's what we're going to be talking about now. So I'll start with just introducing an example to you. Here is a tertiary communication system. That means there's three symbols. And these are the waveforms I'll be associating with each one of the symbols. The first symbol, there's a time of a symbol, which is 3 intervals of time. And during the first 1/3, I have +1 voltage. Second 1/3, I have -1 voltage. And the last 1/3 of the symbol time, I have 0 volts. That's my first symbol. My second symbol is going to be 0, followed by 1 level, followed by -1 level. That is the waveform. It's a piecewise constant waveforms that I'm using. That's the second one. And the third one is going to be level 2 for 1/3 of the symbol interval and -1 for the last 2/3 of the symbol. So time-varying signals, 3 different ones to represent 3 different symbols. Now, I'm going to show you how we can represent these time-varying signals in a vector space. In fact, a vector space of dimension 2. And here, the red one is the first. So somehow, this time-varying signal is going to correspond to this red vector. And the other 2 will correspond to the other 2 vectors I show here, S2 and S3. So what's really going to be interesting is being able to take these waveforms and say, all of our analysis, I don't have to look at what's happening in the time domain. I can actually just look at this vector space representation and do all of my analysis here. And so we're able to take perhaps choices for waveforms which may appear to be extremely different approaches, but we'll see that when we look at their equivalent in signal space, actually their signal space representation is identical, which means that they're going to have the same performance, the same characteristics. So it's a great tool to help us understand what's going on with our modulation choices, our choices of waveform. So I gave you an example so that you know where we're going with this approach, and now I'm going to take you through some more of the definitions and details about what is a signal space and show you how do we go from this collection of 3 symbols into this representation in signal space. So we start out with a basis for the vector space, for signal space. Signal space is a vector space. Vector spaces are spanned by a collection of basis vectors, and the basis vectors in this case is a collection of time-varying signals. So in this case there's capital N. It's a finite dimensional collection of basis vectors. There are n of them, and each one of them is a time-varying signal. Now, if it's a collection of basis vectors, by definition, that means that any vector in the vector space can be represented by a linear combination of the basis vectors, definition of basis vectors. Now, I want to reduce, there are an infinite number of bases, and I want to pick a collection of vectors which are orthonormal because they're easier to work with. What does that mean when we say they're orthonormal? This collection of basis vectors is orthonormal because if I take the inner product, and we see here the notation for the inner product, if I take the inner product of a basis vector with itself when I equals j, when I take the inner product with itself, it equals 1. 1 is the normal part here. It's normalized. So every basis vector has length of 1. And if I take the inner product of 2 different basis vectors, j not equal to I, well, they give me an inner product of 0, which means they're orthogonal. Okay, so the basis vectors, I'm going to assume that there is a collection of basis vectors which describes the signal space. And the signal space, of course, each signal is a time-varying system. And so what I have to do is define, what do I mean by the inner product? You haven't come across that before necessarily. What is the inner product of this 2 time-varying signals? So by definition, I'm going to say that I'm going to take the integral over one simple interval, for the integral from 0 to capital T, of the product of the 2 basis vectors. That is going to be the definition of the inner product. So here's the inner product in this orthonormal basis for the signal space that I am proposing. Well, note that I said it was finite dimensional and I said the dimension was n. At the very largest, n will be equal to m, the number of symbols in the alphabet. However, it is possible that the dimension of the signal space could actually be smaller than m. So that's an upper bound on this finite dimension of a signal space. So this is a space that includes all of the signals in the alphabet. So a signal vector, what does it mean when we have a vector representation of a time-varying signal? That means that, first of all, because this signal is in the signal space, that means it can be written as a linear combination of the basis vectors. That means that each one of my symbols, so here is an I, the ith symbol, can be represented by a linear combination of the collection of n basis vectors. And in fact, this linear combination, we say that each one of the weights assigned to each one of the basis vectors is the coordinate, or the coefficient, of the vector in that dimension. So therefore, I take all of these weights used to create the symbol, and I use them in a vector, in a sequence that represents the vector form of that time-varying signal. So here's a function of time, linear combination of other vectors which are a function of time, but here's the signal space representation, which is just a vector, a collection of numbers. It's these weights. So this is a vector that we can manipulate in all the other ways we've learned how to manipulate vectors in a vector space. Now, of course, how do I get the coefficients? How do I know what the coefficients are? Well, I do the projection of my signal onto each one of the basis vectors in turn. And the inner product of the symbol, inner product with each one of the basis vectors, that will give me the coefficients. We can see that this is the case, that there's self-consistency in these equations, because suppose I take the SI of t and I say it's some linear combination because it's in the space. So I replace the SI of t with, here it is, this linear combination of terms. And I say that the inner product of this SI with, let's say, the kth basis vector. Well, the inner product is a linear operation, and therefore the inner product of a sum is equal to the sum of the inner products. So I can take the sum outside of the inner product, put it on the outside. And so what I get here is the inner product of basis vector j with basis vector k. Now, by construction, these are orthonormal, which means that if j is not equal to k, it's 0. So most of this sum is 0. There's going to be one element which is not 0, and it's going to have inner product of 1 because they're normalized, orthonormal. So that means that this projection is just going to give me the coefficients, the kth coefficient for symbol I. So it is indeed this coefficient in the weighted sum is indeed the result of the inner product projection. So this is how I can find the coefficients for a symbol. So once I have the collections of C, I take the inner product of the symbol I'm interested in, inner product with each one of the basis vectors, and I get the coordinates, and then I put the coordinates into a vector. So now I have a vector representation of this time-varying signal. So what happens if I take the inner product of a signal with itself? In that case, I get something called the L2 norm. I guess I could write it up here. Here's another way. So we have SI, the ith symbol, inner product with itself. By definition, it's the integral from 0 to t of the symbol SI of t squared. And we interpret that to be the signal energy. If we think of the SI of t as being a voltage versus time, which is passed through a unit resistance, then what this equation gives me is a signal energy. But it's also, in vector space, what we call the L2 norm. The L2 norm is the square of the length of the vector. So if I had no square here, that would be the representation for the length of the vector in the vector space. So we can see how this representation in vector space can start giving us some intuition from our geometry, from our geometric approach. So the length gives us an indication of energy. For instance, a longer vector means that there is more energy on that symbol than if a shorter vector which represents a different symbol. So that will be important to us when we want to compare different solutions, because we have a certain budget of energy and we can choose to give most of that energy to some symbols or equal energy to all symbols. You know, we have this choice when we're designing a communication system. Now, when we want to compare the power efficiency of different modulation formats, it will be important for us to compare apples and apples. And in order to do that, what we're going to do is we're going to base that on what we call the average signal energy. And so we're going to have m different symbols, each one with some allowed to have some division of the total energy. And so 1 over m of the sum of these energies is going to give me the average energy per symbol. And that S here means energy, average energy per symbol. And therefore I can compare. When I have this strategy and this average energy per symbol, and I have another strategy, which one gives me fewer errors, which one has a less error. So very important to compare systems with the same average signal energy. So that's great. Now I can represent my signals in a vector space. But how does this relate to the received signal? Because the received signal is the original transmitted signal plus noise. And that's where things really start getting interesting. Because every time I send a symbol, if there was no noise, every time I sent the symbol, that's exactly what I would be received, would be the symbol. And if I looked at the collection of received vectors, there would just be, you know, like if there would just be m. If there were m symbols, there would be like m points in this space. But what happens is each time I send a symbol, there's a different realization of the additive white Gaussian noise. So one time I might have a big hit of noise, and instead of landing exactly on the point which was transmitted, I'm quite a bit away from it. Another time there could be very small noise, and I could fall almost right on the transmitted symbol. So in this little illustration, I'm showing two symbol vectors, and I see a cloud around them. And this cloud is the noise. This is, instead of getting that same point every time it's perturbed a little bit differently, a little bit to the side, and it starts looking like a cloud around the transmitted point. Bigger cloud, more noise. Smaller cloud, less noise. So we can see already some intuition from being able to visualize what is it that's being received. So here is a given received vector. Now, whenever, this is each point represents a received vector. And what is the goal of any communication system? It's to take a given received vector, here's one R, and to choose which symbol was transmitted. So I'm given an R, that's what I observe, it's my test statistic we're going to see, and then I have to decide, which symbol was actually sent. So this is why we're using signal space, and why the impact of noise is going to influence our decision process as it should. So I know that adding noise to the received signal results in this sort of cloud-like reception. So how do I handle the representation of this noise, which I know is of infinite dimension? How do I represent that noise in the signal space? So the way I do that is I take my signal space and I expand it so that it will cover all of the noise, represent the noise correctly. So I think of this as an extension of the signal basis. So I have from C1 to Cn, which is the original collection of basis functions, and now I have to add to them to create an infinite dimensional space, which will be able to represent the noise which is added. Because remember, I'm choosing m symbols, I'm giving m time varying representations for those symbols, and because it's a finite number, I can represent them in a finite dimensional space. But the noise is a random process, and it can just go anywhere. It can look like anything, so that's why it's infinite dimensional. Fine, so what I do is I add basis vectors to expand the space until it covers all the noise that could be generated. So that means that if I look at the representation for a vector of noise, it will have an infinite number of coefficients, an infinitely long vector. And how do I find out what are each of the coefficients of this vector representation of the noise contribution? Well, if I have n of t as being the noise contribution in the received signal, then I would just project this noise onto each one of the basis vectors. I take the inner product of that random process, which is a time-varying signal. I take the inner product, I take the integral from 0 to t of that noise with each one of the basis vectors. And that gives me a number after I do the integration, and those are the coefficients inside of this vector representation of the noise. So I did this basics extension. So what does that mean in terms of the vector for each one of the symbols? I have m symbols, and I've already found the coefficients from 1 to n for each one of those symbols, what the coefficients are, and now I've extended the bases. Well, that's okay, because my signal falls in those first n basis vectors. That covers all of the symbols. That was the definition. That's what these basis vectors were. That means that every time I do the projection of this symbol onto one of the extended basis vectors, I'm always going to get 0, because it's not anywhere else. It's in that original signal space. So okay, so now it's infinitely long, but I'm just adding a bunch of zeros. So it's the same coefficients as before, but now I'm adding zeros to the vector for each one of the symbols. So the received signal now, I know that it's the symbol sent plus this random process that I have on the noise, and that I can represent this now in vector form. So I don't have to do time domain signals. I can just look at the vectors in the signal space that I've created. So where are we so far? Now we are able to represent the received signal. The received signal is the sum of the symbol that was transmitted and the random noise process. And even though this random noise process is an infinite dimensional space, I start by forming the signal space, which just covers the symbols, and then I add to that enough basis vectors so I can cover all the noise. So that means that this received vector, which is a function of time, can be represented in signal space. And so this signal space representation is a vector, and it's the vector of the symbol which was transmitted plus the noise.